Есть более... Так, сейчас. Есть более экономные комплексы, которые приходят из CW комплексов. Да, значит, да, значит, про них мы сегодня поговорим. Okay, are we ready? Is this thing on?
Well, the sound is fine, but the camera is frozen.
The camera is not working.
Yeah, but I guess.
Well, the camera records me, which is not particularly interesting, but also the blackboard, which is more interesting. So let's wait a little to see if we can get it working. We saw the universal coefficients theorem, and there's one thing which I mentioned, but we didn't discuss it in detail. The splitting is not natural. The splitting is not functorial. The splitting of what? Let's let's do an example, and also let's remember what actually the theorem says. So I take a chain complex of three Z modules. It doesn't have to be a singular chain complex of anything. And I have a split long exact sequence. Now, in the middle, I have the homology of the complex tensor G, where G is an abelian group. And what do I have on the left, and what do I have on the right? Okay, Hn C tensor G. And on the right I have Tour, or Tour 1 of Hn and G. Yes, thank you. it's supposed to be minus 1. Okay, now there's a subgroup here which maps isomorphically to Tor Hn minus 1G. But the subgroup cannot be chosen in a functorial way. In other words, if we know Hns, we know Hn of C tensor G, but not functorially. So let's reflect upon this for a minute. We know the value of this functor on any object, but we do not know the functor. And this happens. So to know a functor, to determine a functor, it does not suffice to determine its values on the objects, which, well, which is not particularly surprising, but here's an explicit example. Okay, well, let's well, let's consider the following chain complex of 3 abelian groups, and inside it I consider a subcomplex C C prime, which is just Z in degree I. Now the quotient will be Z in degree I plus 1. Okay, well, let me take G G to be Z by N. No. Okay. Now, the complex C tensor G will become this with 0 differential. No big surprise here. Well, the differential is 0, so the cohomology groups are, or the homology groups are exactly the same. sorry, it's homology. The homology groups of what? Of this complex. Meanwhile, the homology groups of C are as follows. In degree I plus 1 we have nothing, because in degree I plus 1 we don't have any cycles apart from 0, and in degree I we have z by n. Very well. So let's see where these groups come from. So this group HI comes from the tensor product. And this group comes from Tor, which is basically straightforward from what we've seen. None of these two groups can come from anywhere else. Alice, does this make sense? We have only one, integrally, we have only one group. So this z by n cannot come from Tor. Tor would be Tor of hi minus 1, and hi minus 1 is 0. And for the same reason, this group cannot come from the tensor product. The tensor product would be the tensor product of hi plus 1, but we don't have anything in degree h plus 1 integrally. Okay, now well, the homology of C prime and C double prime are the same as the complexes themselves, because the complexes are very simple. And now let's see what happens. Let's consider the map from the homology of C tensor G to the homology of C double prime tensor G. Here we have z by n, which comes from Tor. So this z by n comes from Tor, and what is this? What is its image in the homology of C double prime tensor G? In C double prime tensor G, everything comes from the tensor product. Well, there isn't much. There is just this z in degree I plus 1. But it comes from the tensor product. And what does the homology map do? Well, it takes this z by n isomorphically to this z by n. So let me write this down. So for C prime and C double prime, we have, if we tensor either of these by Z by n, we get Z by n as homology, and both those Z by n's come from the tensor product. So the homology map takes the torque contribution to the contribution of the tensor product. In other words, the splitting is not functorial. And similarly for the other exact sequence, which expresses the cohomology in terms of hom and ext. Does this make sense? Of course, the question is, this complex is purely algebraic. Is there a way to realize it topologically? Well, we know that there are singular chain complexes which work for all spaces, but as I said a few minutes ago, on the nose, those singular chain and co-chain complexes are of an enormous size, and in particular. There isn't a space for which we have this as the singular chain complex. So we will now look at more economical chain-like complexes. In other words, we will construct chain complexes for a class of spaces, not for all spaces, and those chain complexes will be functorial with respect to some maps, not all maps, but those complexes will be much smaller than the singular chain complexes. And for those chain complexes, we will realize the example I've just erased as the chain complex of a very simple space called the Moore space. Let's first of all recall what a CW complex is. Confusingly, there are CW complexes which are spaces of some particular type, and there are chain and co-chain complexes which are complexes of abelian groups. And well, hopefully at every moment it should be clear which complexes I'm talking about. So let's recall the definition of a CW complex. A CW complex is a Hausdorff space, and a family of continuous maps such that the following conditions are satisfied. Okay, let me erase the index alpha here. We have just one unit disk, and but lots of maps from the unit disk to X. Well, the first condition is as follows. F induces a homeomorphism between the open unit disk and its image. In other words, the map is injective when restricted to the unit disk, and moreover, it's a homomorphism. Let's denote the image of F alpha restricted to the interior, to the open unit disk by E alpha. In particular, each E alpha has a dimension. We take the dimension of E alpha to be just n. The second condition is this. Every element of the closure of a cell, which does not belong to the cell itself, belongs to some other cell of strictly lower dimension. The next condition says that set theoretically, not topologically, set theoretically, X is the disjoint union of all E alphas. And if the number of cells, which is the same as the number of those maps, is finite, then we don't need any more conditions. But in general, we do. And there is also there are two more conditions which actually are the C and the W in this term CW complex. Condition C. Condition C says that the closure of every cell is contained in a finite union of cells. And condition W simply says that well, let me put a closed instead of open. A subset of X is closed if and only if its intersection with the closure of every cell is closed. Well, in one direction, this is automatic. If we have a closed set and intersect it with another closed set, the result is a closed set. No surprises. But we require that the reverse implication should also be true. Or equivalently, so this is for every alpha. Equivalently, we could require that the preimage of A under F alpha should be closed in Dn for every alpha. Well, this was just a reminder. There probably was something about CW complexes in topology 1 or in basically I don't know what this course is called at the moment. I think it's an introduction to discrete and continuous mathematics. It doesn't matter. Introductory topology. The introductory topology course is supposed to have something about CW complexes. Okay, so let's just well, let me look at those two conditions C and W, and see if there is a way to construct an easy example of a space which satisfies all conditions except C and all conditions except W. Okay. Does anyone remember a counterexample which shows that condition C is necessary? Well, let's take X to be the unit disk in the plane. And we consider as cells all points of the boundary and the interior of the unit disk. Well, for the points on the boundary, there is just one map from the standard point to any given point. So the map F alpha is straightforward. For the interior, the map F alpha is just the identity map of the disk. And as you can check, all axioms are satisfied, but except axiom C. And similarly, do you know an example in which all axioms are satisfied except W? In other words, an example which shows that W is necessary. Well, there's a standard example of the Hawaiian earring. In other words, is the union of all circles centered at the point at the points 0, 0, 1 by n, and the radius, well, let me take 1 by n as, sorry, center 1, yes, center 1 by n. And the radius is also 1 by n. In other words, all those circles pass through the origin. And let me consider the following cell decomposition. I have just one zero cell, which is the origin, and countably many one cells, which are obtained by taking the nth circle and deleting the origin. Again, it's straightforward to construct the maps F alpha. For the point, the map is there is just one possible map from the standard point to this given point, and then for the one cells, I just take some standard segment, some standard line segment, and map it to the circle as shown in this picture. And all axioms are satisfied apart from the W, the last one, the axiom W. Why? There are not enough open subsets in this topological space in order for it to be an infinite wedge of circles. So an infinite wedge of circles is a bona fide CW complex. But this is something which resembles a wedge of circles, but isn't. So and the space is called the Hawaiian earring, and the Hawaiian earring is not homeomorphic to an infinite wedge of circles. Why? Well, for one thing, the infinite wedge of circles is not metrizable. While the Hawaiian earring is a subset of R2, and the topology induced by the standard topology of R2, and hence is metrizable. Okay. This was just a brief reminder about CW complexes. Now, are there any questions? Is there anything else we want to recall about CW complexes? if I have a CW complex, I define the nth skeleton to be the union of all cells of dimension n or less. And all skeleta are CW subcomplexes. And let me just recall that a CW subcomplexes is a closed subset, which is a union of cells. And it follows from one of the axioms that xn for every n is a subcomplex. Now, it follows from point set topology that if I take a complex, a CW complex and a subcomplex, then the quotient space, the complex by the subcomplex, is also naturally a CW complex. If we have a CW complex, we will now define cellular chain and co-chain complexes with coefficients in an abelian group G. Okay, now let's define those groups. This follows automatically from the fact that the unit disk is compact and X is Hausdorff. The image of F alpha is compact, and since X is Hausdorff, it's also closed.
So the closure of P alpha is just the image of F alpha, am I right?
Yes. Okay, now I have defined the groups calligraphic C, N, and calligraphic C, upper N. Okay, now what is xn by xn minus 1? Well, this is simply a wedge of spheres of dimension n for all alpha, such that n of alpha is n, which is, well, more or less straightforward from the definition of a CW complex. So basically here we have a direct sum of some number of copies of G, and similarly here we have the direct product of the same copies of G. Why? Because we know to calculate how to calculate the homology and cohomology of a wedge of spheres. Now I want to define the differential. From now on, I will stop writing G, which is assumed to be the same everywhere. I define the differential as the connecting homomorphism in the long exact sequence of the triple xn, xn minus 1, xn minus 2. Now, the question is, well, there are two questions. First of all, did we talk about long exact sequences of triples? And if we did, does anyone remember it? Okay, so let's say something about those. Okay, suppose I have a space and suppose inside the space I have two subspaces which are contained one inside the other. Then I have the following short exact sequence of chain complexes, where C C lower star of x comma a is simply the quotient of C lower star of x by C lower star of a. Does this make sense? Okay, now if we apply the functor tensoring by G, and also if we apply Hom into G, we still get short exact sequences of chain complexes. Why? Well, because basically all those chain complexes are free, and all maps take generators not only free. Each of these has a preferred basis obtained from singular simplices. More precisely, here we have a natural basis which is obtained by taking all singular simplices in A which do not such that the image is not entirely contained in B, and so on. So we well, it's using this, it's straightforward to check that we still get, although tensoring by G and Homing into G is none of them is an exact functor. In this case, there aren't any problems. We get short exact. We still get short exact sequences, and then we apply well, the usual trick. If we have a short exact sequence of chain complexes, we have a long exact sequence of the homology groups or cohomology groups. And so, in particular, if we take this as a triple, we get this map. Okay. Do you want me to write those long exact sequences explicitly, or is it already clear what they look like? Okay. So the default assumption is it's already clear, but if it isn't, please let me know. Okay, now I have defined the differential, and I want to see and in the cohomological case, the definition is exactly the same, except the differential will go in the opposite direction. Okay, now from this definition, it's not at all clear why the differential squares to 0. It's not clear either that the homology of the resulting chain complex will be isomorphic to the homology of X. So we need to prove this. The claim is we do indeed have delta squared equals 0, and so we get a chain complex, and the homology groups of the resulting chain complex are the same as the homology groups of X. And moreover, this is an isomorphism of functors, but functors of what? Well, the right-hand side is functorial in all continuous maps. This is clear. What about the left-hand side? Well, the complex calligraphic C is only functorial with respect to cellular maps. So we can't expect more, but we can expect this. And as we'll see in a minute, we do indeed have this isomorphism which is functorial. Okay. So what do we do? Shall we prove this first, or shall we have a break first? Okay. Well, basically the proof follows from a diagram. So let me maybe draw the diagram, and then basically I invite everyone to think about the diagram, and we'll discuss it after the break. Okay. So we have n plus 1 n minus 2, n plus 1, x, n minus 2, 0, 0, h n x n minus 1. So this is the n plus first chain group. Now I need the nth one. The nth one is here, hn of xn mod xn minus 1. Okay, hn xn plus 1 xn. And this is, well, this is the same. Okay, well, let me explain what happens in this diagram. Basically, this diagram contains everything we need. But first of all, what do we have here exactly? Well, we have 2 rows. What about the top row? The top row is is a part of the long exact sequence of the triple xn plus 1 xn xn minus 2. What about the bottom row? Well, the bottom row, in the bottom row, we have a segment of the long exact sequence of xn plus 1, xn, xn minus 1. So this is the top row and the bottom row. What about the column? In this column, we have again the long exact sequence of the triple xn, xn minus 1, xn minus 2. Okay. Now,
Why did you write instead inequality in the first column?
yes, basically, this triple maps into this triple. But on the level of the couples, we have the identity map. So this is the identity map.
But one here from plus one homology group, another is.
Oh, sorry. Yes, yes, you're right. It's supposed to be a plus 1. Thank you. Okay. Now, does the diagram make sense on the level of the definitions? Well, let me just explain this 0. This 0, what is it? Well, this 0 is hn of xn minus 1, comma xn minus 2. But xn minus 1, this homology group is the same as the nth homology of a wedge of n minus 1 spheres. So the result is 0. What about this 0 here? Let's see what it is. It's hn again of xn plus 1 mod xn. And again, we have what we have here is the nth homology the reduced nth homology of a wedge of n+1 spheres. And the result is 0. So we have drawn the diagram, and we understood why we have 0 in this place and in this place. Well, I think now we deserve a break. And after the break, we'll take a look at the diagram again and see why it follows from this diagram that we have this isomorphism and this equality. Are there any questions? Let's have a 20-minute. What does the diagram tell us? Well, first of all, we have delta squared equals 0. Why? Because delta squared is what? It's the composite of these two maps. Well, this much is clear, but since this map is an isomorphism, I may as well consider the composite of these three maps, which is the same as going from here to here, then here, and this composition is 0 because the row is exact. Second of all, what are the n cycles? The n cycles of Zn of calligraphic C. Well, my claim is the n cycles, what are they? The n cycles is the kernel of this map, but here we have 0. So the kernel of this map is isomorphic to Hn. Hn of what? Hn of xn plus 1, no, xn minus 2. And thirdly, what are the n boundaries? The n boundaries are isomorphic to the image of h n plus 1 x n plus 1 x n in, well, in the same group, in Hn of xn mod xn minus 2. Well, by definition, the co-boundaries live here, but they also live the boundaries, not the co-boundaries, the boundaries. The boundaries live here, but they also live in the group of cycles, which is in fact this group. So instead of considering the image of this here, I may as well consider the image of this group here, because the next map, this one is injective. And 2 plus 3 together imply that the Zn by Bn is isomorphic to this group. Why? Well, because the top row is exact. I have this group, and I quotient by the image of this group. What do I get? By the exactness of the top row, I get the image of this Hn inside this Hn. But the image of this Hn inside this Hn is all of this Hn. Why? Because there is a 0 on the right. Hn xn plus 1 xn minus 2. Okay. Now we've extracted all useful information there is in this diagram. Now we need two more ingredients. Ingredient 1, I claim that this is the same as Hn of x. No, sorry, this is supposed to be n plus 1, same as here. N plus 1. Just n plus 1. Why? Well, we have this this isomorphism. Why? Because H because H x n minus 2 has 0 cohomology, homology, 0 homology in degrees n minus 1 and n. And this is something one can prove by induction on. One can prove by induction, meaning if we have a finite dimensional CW complex, then the homology vanishes in all degrees which are greater than the dimension of the complex. And a proof is by induction starting from dimension 0, then using the long exact sequence of the couple, ith skeleton, I plus first skeleton. Does this make sense? Does everyone understand what I mean here, or I need to write it in more detail? Okay, so if there are people who do not quite see why I can claim this, please let me know. And finally, the last thing that I need is this isomorphism. Hn of xn plus 1 is the same as Hn of the whole of x. Why? Well, let me write it like this. I can pass from xn plus 1 to xn plus I for every I greater than or equal 1. Again, using the long exact sequence of the couple xn plus I, comma, xn plus I plus 1. And here, at the final step, I use the fact that homology commutes with direct limits. In other words, I can replace, well, this sequence of groups is stable in I. It does not depend on I. So I can replace each of those groups by the direct limit, where all maps are induced by the inclusions. Okay, but what is this direct limit? The direct limit of the homology groups is the homology of the direct limit. And here we use we use the following thing. It follows from the W axiom that the direct limit of the spaces xn plus I is just x itself. So I finally arrive where I wanted, namely the group, the cellular homology group, is isomorphic to Hn of x. And well, it follows from the construction that everything is functorial with respect to proper maps. Are there any questions? And it works in the same way for cohomology, except the arrows will go in the opposite direction. Okay, now let's see how the cellular chain complex works in examples. And at this point, I would like to erase everything, so please let me know when you're ready. Okay. So let's see how one can do calculations with the cellular chain complex. Okay, now the nth chain group is well. Let me put a tilde here, although this doesn't really matter as soon as n is greater than 1 or even 0. We have this. Well, for simplicity, let's take z, g equals z. The case of arbitrary g is obtained by tensoring everything by g. So if we know how to calculate the singular chain complex for g equals z, we will know how to calculate it for an arbitrary g. Now, we have this isomorphism. Well, to specify it, we we need to choose we need to make some choices. Namely, let's choose a generator of Hn Sn for every n, such that, well, let me call this generator, I don't know, An. Bad notation, yes, but I can't think of anything better at the moment. Such that An goes to An minus 1 in the following the following sequence. Hn of dn by Sn minus 1 to Hn minus 1 Sn minus 1. And we also need to choose an identification of the quotient space with Sn. Let's just choose this homeomorphism in such a way that it preserves the orientations. And let's equip every sphere by the orientation which is induced from the Euclidean space. Okay, now. Once I have those identifications, I have generators for every. I have a preferred generator for each of the groups Hn of so this Sn alpha is in fact dn by N minus 1. So as soon as I've made these choices, I have a preferred generator for each of those groups. So I get an isomorphism, an explicit isomorphism. Now I want to calculate the differential. Well, let me denote the distinguished generator by A alpha. Here, alpha runs through the set of all cells of dimension n. To calculate the differential, it suffices to calculate it on the generators. So I take the generator A alpha, and then, basically, by definition, I can write this formula. But in this formula, of course, there are those integer numbers which are called the incidence coefficients of the cells E alpha and E beta, and the question is what are they? How to calculate those? And now we recall that if we have E alpha, we also have a map which we denoted F alpha from the standard n disk to X. Very well. We can restrict F alpha to the boundary S n minus 1. This map will go S minus 1 to X, yes, but in fact to X n minus 1. In other words, the structure map F alpha takes everything takes the boundary to the n minus 1 skeleton of X. Very well. Well, again, so far no surprises, or I think there aren't, but if there are, please let me know. Okay, now we have a map from xn minus 1 to xn minus 1 by xn minus 2. Again, no surprises. And we know that this thing is a wedge of spheres. Well, let's collapse everything, all spheres except one particular one. So here we collapse all spheres except one. What do we get? Now let's take this map and compose with this map. Notice that after we make all these identifications, we get a map from the standard sphere to the standard sphere. In other words, we get a map from Sn minus 1 to Sn minus 1. And the incidence coefficient is just the degree of the resulting map from the n-1 sphere to itself. Well, let's see how this works in a couple of examples. Yes, so we have alpha and beta, and for such that the dimension of E beta is one less than the dimension of alpha. And we want to calculate this number. And it turns out that the number is simply the degree of the map from the n-1 sphere to itself, which is well defined. Okay, now let's do the 2 torus the 2 torus has 4 cells. I've drawn them. On the board. There are the 0 cell, the 2 cell, and 2 1 cells. I think this picture is probably familiar to everyone. Otherwise, please let me know. Well, the differential from 0 to from degree 1 to degree 0 is more or less straightforward, and the answer is if I have a one cell such that the endpoint is the same as the starting point, then the differential is 0. Otherwise, it's the difference of the endpoint minus the starting point. So what about d2? D of E2. Well, I have the standard S1 inside of standard D2. Let me choose orientations on the one cell and on the other one cell. And this is something I need to choose in order to get a map of to get a matrix, not just a map of the cohomology group, but a matrix. I need to say orientations are the same as isomorphisms are the same as isomorphisms between the one cell with the endpoint collapsed and standard and the standard S1. Okay, now I want to the structure map which corresponds to the 2 cell is simply a homeomorphism between the standard 2 disk and the square, composed with the map from the square to the torus. Does this make sense? So, in other words, I'm not writing the structure maps, but these are clear from the picture. To get the structure map, I just take the standard 2 disk. I need to. It's part of the definition. I identify the standard 2 disk with the sphere, with the square in an orientation preserving way. And then I take the map from the square to the torus. What do I get? I get a map from the standard 2 disk to the torus. And then then I can restrict the resulting map from the two-disk to the torus to the boundary of the two-disk, which is the circle. What do I get? I get a map from the circle to the wedge of two circles. How does this map work? Well, it works as shown on this picture. So the circle can be thought of as the boundary of the square. I take this quarter, I map it to the, sorry, this is supposed to be a E11, E12. I map it to E11, then the next portion goes to E12, then E11. But this time, when I take the third quarter, I map it. I go in the opposite direction along E11, and same here. E12. So this is the map from the circle to the wedge of two circles. Well, what happens if I collapse one of the circles? I get the following map. This time I get a map from the circle to the circle. How does it work? It works the following way. I again partition the circle into four parts. Then, when I'm on the first part, I run around the circle once. Then I stand still, because the second circle has been collapsed. Then I run around the same circle in the opposite direction. Then I stand still. So I get a map from S1 to S1, which works as I've just described. Well, it has degree 0. And it doesn't matter which circle I collapse. Meaning, if I collapse the first circle, I get degree 0, and if I collapse the second circle, but keep the first circle non-collapsed, I also get degree 0. So the chain complex I get is as follows. Basically, Z, I get Z in degrees 0 and 2, Z plus Z in degrees in degree 1, and and both differentials are 0. Okay, now what happens if I take the Klein bottle? If I take the Klein bottle, the recipe is exactly the same, except the map meaning I still get two maps from the circle to the circle, but these will be as follows. The first map will be exactly as in this example. On the first, when I'm in the first quarter of the circle, I run around the circle once, then stand still, then run once in the opposite direction, then stand still. And what happens in this example? I first stand still, then I run around the circle once, then I stand still, and then I run around the circle, but in the same direction. So the resulting map from so let me so so a wavy line means I stand still. So, and the first so the first map from the circle to itself will be the same. But the second map will not be the same. The second map from the circle to itself, in this example, will not be the same. It will work as shown here, meaning stand still for a while, then move around the circle once, around the target circle, then stand still, and then move again around the target circle in the same direction as the first time. And the result is a map of degree 2. And so we get the following answer. Well, the differential from degree 1 to degree 0 will still be 0, but the other differential from degree 2 to degree 1 will not be 0. It will take a generator to an element which has coordinates 0, 2 in some basis. So H1 of the client bottle is Z plus Z by 2, which we knew already. But now we have another confirmation. Okay, does this make sense? And there are more examples, for example, one could explicitly calculate the cellular chain complexes for real projective spaces and, in fact, many other spaces. And I think there are, well, some of those are in the problem sheets, so we will not say any more about those. But there is one example I wanted to mention. HI N H not equal I is 0. M divided by N I. Okay, now this space is uniquely defined if, up to homotopy equivalence, of course, if I is greater than 1. And let's also require that the space should be simply connected if I is greater than 1. Well, there is an explicit way to construct the space. Namely, we take the standard I sphere and we attach we attach the standard I+1 disk to it using a map of degree n. Well, can one give me an example of a simple example of a Morse space for n equal 2? Yes, very good. For example, M, it's a Morse space because M z by 2, 1. Is not uniquely defined. We have one. In order for it to be unique, we need to have I. We need to have I greater than 1. Anyway, for any I, we can do this construction, which gives RP2 if I is 1 and n is 2. And the cellular chain complex of this construction is Z, where the map is multiplication by n, which is more or less straightforward from what we've already seen. So, in other words, we have realized the complex we started with as the cellular chain complex of this space. Do you remember in the very beginning there was a complex C, C prime, and C double prime. Well, this complex is exactly C, the one we started with. Now, C prime is the cellular chain complex of the sphere Si, and C double prime is the cellular chain complex of the sphere Si plus 1. So, in other words, what we said in the beginning about chain complexes applies to spaces too. Meaning So the splitting in the universal coefficient theorem is not functorial. For spaces, just as it isn't for simply chain complexes. Okay, well, I think we've run over time again. So, are there any questions?
Can every chain complex be represented as the cellular complex?
There are some difficulties. For example, for cellular chain complexes, we can't have anything in negative degrees. But otherwise, if we require that the non-zero components start in degree 2 or 1, then I think yes. Are there any more questions? There is one other problem. The differential from degree 0, from degree 1 to degree 0 cannot be arbitrary, because there aren't any degree n maps from the zero-dimensional sphere to itself. So there are some restrictions, but other than that, it works. Are there any questions? Okay, well, then we'll see each other next week, and next week we'll talk about products, well, products in various senses.